On a hot summer afternoon, the temperature inside an uninsulated attic can reach 140 to 160 degrees Fahrenheit, even when outdoor temperatures measure merely 85 to 95 degrees. That trapped heat radiates downward through ceiling insulation into living spaces below, substantially increasing air conditioning loads and driving cooling costs far higher than outdoor conditions alone would suggest. The attic heat problem affects virtually every American home, regardless of insulation quality, because even excellent ceiling insulation cannot fully block the thermal transfer from extremely hot attic spaces into living areas below. Traditional gable vents and ridge vents help modestly by allowing some hot air escape, but rely entirely on natural air movement that often fails to provide adequate ventilation during calm, hot weather when cooling needs are maximum. Powered attic ventilation fans solve this problem actively by mechanically extracting hot attic air and replacing it with cooler outdoor air, dropping attic temperatures by 30 to 50 degrees during peak cooling periods. The resulting reduction in downward heat transfer cuts air conditioning runtime by 15 to 30% in most hot climate homes at equipment costs of $200 to $600 and annual operating costs of $20 to $60. Understanding how attic ventilation fans work, what approaches deliver greatest benefits, and how to integrate these systems with overall home cooling strategies reveals one of the most cost-effective cooling interventions available to existing homes. The fundamental physics of attic heat accumulation explains why conventional passive venting often fails to manage attic temperatures effectively. Solar radiation heats roof surfaces to extreme temperatures during sunlight hours, with dark asphalt shingles reaching 160 degrees or higher. The heat conducts through roof decking into attic air, raising attic temperatures substantially above outdoor ambient conditions. The trapped hot air stratifies in attic spaces with hottest temperatures concentrated near peaks. Passive vents rely on thermal buoyancy and wind pressure to drive air exchange, but often deliver inadequate air movement to meaningfully control attic temperatures during calm, hot weather. The performance gaps between passive venting and actual attic heat loads have been well documented but remain poorly addressed by conventional construction practices. The original attic ventilation fan technology dates to the 1950s, when rural, Southern homes began adopting electric-powered fans to manage attic temperatures before air conditioning became widespread. The earliest fans mounted in gable ends and drew air through opposite gables or soffit vents, providing substantial attic cooling at modest energy consumption. The technology preceded widespread air conditioning adoption by 2 decades, representing transitional cooling approach that improved comfort before mechanical cooling became affordable. As air conditioning adoption grew during the 1960s and 1970s, attic fans faded from mainstream construction despite continuing to deliver substantial cooling benefits when properly applied. Dr. Calixta Santillan Duran, a Peruvian-American building science researcher who has studied attic ventilation performance across diverse climate zones, has documented how properly designed powered attic ventilation can reduce ceiling heat gain by 30 to 50% during peak cooling periods. Her research at major Southwestern universities examines comparative performance of passive versus powered attic ventilation across typical American home configurations. The research findings provide evidence-based foundation for understanding which approaches deliver greatest benefits in specific circumstances. The scientific foundation supports design decisions that often conflict with conventional construction practices, emphasizing passive venting alone. The various attic ventilation approaches span substantial range from simple to sophisticated. Gable-mounted fans provide straightforward installation in homes with existing gable vents, requiring modest electrical wiring and no roof penetration. Roof-mounted turbine vents powered by wind provide partial mechanical ventilation without requiring electrical connections. Electric roof-mounted fans provide reliable mechanical ventilation independent of wind conditions but require roof penetration. Solar-powered attic fans eliminate electrical consumption by powering fans through integrated photovoltaic panels. Whole-house fans mounted in ceiling planes provide dual functionality serving both attic ventilation and whole-home cooling. The approach selection balances costs, installation complexity, and performance requirements for specific applications. Adekunle Oyelaran Olaniyi, a Nigerian-American residential HVAC consultant who has installed attic ventilation systems across diverse homes in hot climate regions, has documented how proper fan sizing and installation substantially affect actual performance compared to theoretical maximum benefits. His installation experience demonstrates that undersized fans provide inadequate ventilation, while oversized fans waste energy through excessive operation. The sizing matching fan capacity to specific attic volumes and climate conditions produces substantially better outcomes than generic sizing rules applied uniformly across diverse home configurations. The professional design input often delivers value exceeding its modest costs. The thermostat control sophistication substantially affects attic fan operation, efficiency, and effectiveness. Simple thermostats activate fans at set attic temperatures without responding to outdoor conditions, sometimes operating fans counterproductively when outdoor temperatures exceed attic temperatures. Differential thermostats activate fans only when outdoor temperatures are below attic temperatures, ensuring that ventilation actually cools rather than heating attics. Humidity controls prevent fan operation during humid conditions when air exchange could introduce moisture problems. The control sophistication substantially affects both energy consumption and cooling effectiveness, supporting investment in quality control systems over basic alternatives. The solar-powered attic fan technology deserves particular attention because it eliminates operating costs entirely through integrated photovoltaic panels. Solar attic fans generally operate only during sunlight hours when attic cooling needs are maximum, matching operation timing with cooling needs automatically. The integrated panels provide adequate power for typical residential attic fans without battery storage or grid connections, substantially simplifying installation. Federal tax credits for solar installations apply to solar attic fans, substantially reducing net costs. The solar approach represents emerging mainstream option that eliminates operating cost concerns affecting electric-powered alternatives. Now for the obstacles and limitations affecting attic ventilation fan adoption. First, the installation complications in existing homes affect retrofit applications substantially. Adding electric fans to existing attics requires electrical circuit extension that may involve substantial wiring work. Roof-mounted fans require roof penetration that some homeowners resist due to leak concerns. Gable-mounted installations require existing gable vents of appropriate size or modification of existing vents. The installation variability affects both costs and complexity for different home configurations. Second, the potential conflict with air-conditioned homes can produce counterproductive results in some applications. Attic fans drawing makeup air from conditioned living spaces instead of outdoor soffit vents pull cooled air into attics for exhaust, effectively pumping air conditioning outside. Inadequate soffit ventilation causes this problem in homes where fan exhaust capacity exceeds soffit inlet capacity. The makeup air problem requires careful soffit sizing or use of alternative approaches like whole-house fans designed for conditioned air contexts. Third, the humidity introduction during certain weather conditions affects attic moisture management. Attic fans drawing humid outdoor air into attics can increase attic moisture content during humid weather, potentially creating mold or wood rot problems in attic framing. The humidity sensitivity particularly affects hot, humid climates, where attic ventilation and moisture control priorities sometimes conflict. The humidity controls on quality thermostat systems address this concern, but add complexity to fan control systems. Fourth, the noise considerations affect some installations. Powerful attic fans produce meaningful noise that can disturb nearby occupants, particularly during nighttime operation. Fan motor noise transmits through attic framing into living spaces below, sometimes creating acoustic problems that didn't exist before fan installation. Quality fan selection with variable speeds and proper mounting substantially reduces noise compared to basic alternatives, but noise sensitivity remains design consideration in some contexts. Fifth, the aesthetic objections affecting roof-mounted installations deter some homeowners. Roof-mounted fans add visible elements to otherwise clean roof surfaces, affecting exterior home appearance. Gable-mounted alternatives preserve roof aesthetics but require compatible gable configurations. Low-profile modern fan designs reduce aesthetic impacts compared to older, bulky alternatives but don't eliminate appearance changes entirely. Despite these considerations, attic ventilation fans deliver substantial cooling benefits at modest costs for appropriate applications and deserve serious consideration for hot climate homes with existing attic heat problems. The economic analysis of attic fan investment produces strong returns for appropriate applications. Installation costs of $200 to $600 combined with annual operating costs of $20 to $60 produce annual cooling savings of $100 to $400 in hot climate applications. Payback periods typically range from 1 to 5 years, with continuing benefits across fan service lives of 15 to 25 years. Solar-powered alternatives eliminate operating costs entirely, while federal tax credits reduce net installation costs, substantially improving economics for homes with appropriate roof orientations for solar panels. Winifred Kamau Wanjiku, a Kenyan-American residential energy consultant, has documented how attic ventilation investments deliver superior cost-effectiveness compared to many alternative cooling efficiency improvements. Her analysis shows that attic fan installations can reduce total cooling energy consumption by 15 to 30% at fraction of the capital investment required for comparable improvements through window replacement or HVAC upgrades. The cost-effectiveness particularly favors attic ventilation in efficiency upgrade priority sequencing, supporting installation ahead of more expensive alternatives in appropriate applications. The radiant barrier integration with attic ventilation produces synergistic performance improvements. Radiant barriers reflect solar heat away from attic spaces, while attic fans exhaust whatever heat still accumulates. The combined system addresses heat, gain prevention, and heat removal, simultaneously achieving substantially better attic temperature management than either approach alone. Installation costs for combined systems remain modest compared to comprehensive home improvements. The integrated approach represents emerging best practice for hot climate attic management that extracts maximum benefits from complementary technologies. The comparison with alternative cooling improvements highlights attic ventilation's distinctive cost-effectiveness. Additional ceiling insulation costs $1,000 to $3,000 and reduces heat gain modestly. Complete air conditioner upgrades cost $4,000 to $8,000 and deliver efficiency improvements across entire cooling loads. Attic ventilation fans cost $200 to $600 and reduce cooling loads substantially through direct attic heat management. The cost per benefit comparison favors attic ventilation as priority efficiency upgrade for homes with substantial attic heat problems, supporting installation ahead of more expensive alternatives in appropriate sequencing. The whole house fan variation provides substantially different cooling approach that uses evening cool outdoor air, to cool entire homes rather than merely attics. Whole house fans draw air from windows throughout the home and exhaust it through attic spaces, providing substantial air exchange and evaporative cooling sensation during cool evening hours. The combined attic ventilation and home cooling functionality delivers greater total benefits than dedicated attic fans, though with higher installation costs and more complex integration with home operations. The whole house fan approach particularly suits climates with cool evenings where nighttime ventilation can substantially reduce next-day cooling needs. Johan Andersson Nilsson, a Swedish-American building systems consultant, has documented how whole house fans in appropriate climate applications can reduce total summer cooling energy consumption by 50 to 80%. Compared to conventional air conditioning-only approaches. His project experience demonstrates that whole house fans combined with good insulation and thermal mass can provide adequate cooling for moderate climate conditions without any compressor-based air conditioning. The proven performance validates whole house fan adoption as mainstream alternative to central air conditioning in appropriate climate applications. The climate-specific applications of attic ventilation vary substantially across American regions. Hot, dry climates with extreme daytime heat benefit most substantially from both attic fans and whole house fans. Hot, humid climates benefit from attic fans with humidity controls, but face complications with whole house fans during humid evenings. Moderate climates benefit from whole house fans more than attic fans, using nighttime cooling capabilities extensively. Cold climates benefit minimally from attic fans because summer cooling loads are brief and modest. The climate adaptation determines optimal ventilation emphasis across diverse American regional contexts. The research on long-term performance of attic ventilation systems shows generally favorable results with quality equipment. Modern fan motors typically last 15 to 25 years before requiring replacement. Control components last 10 to 20 years. Solar panels on solar-powered fans maintain performance across 20 to 25-year service lives. The modest long-term maintenance costs combine with substantial operational benefits to deliver favorable lifetime economics. The durability supports attic ventilation as long-term component of comprehensive cooling strategies rather than temporary solutions requiring frequent replacement. The building code considerations for attic ventilation generally support mechanical fan installations as compliance alternatives to passive venting requirements. Most jurisdictions allow powered ventilation as equivalent to required passive ventilation square footage. Some jurisdictions explicitly encourage powered ventilation through efficiency program incentives. The regulatory environment generally supports attic fan adoption without imposing significant barriers that affect many other efficiency improvements. The regulatory simplicity supports widespread adoption across diverse housing contexts. The utility rebate programs for attic ventilation vary substantially across different utility territories. Some utilities offer rebates of $50 to $200 for qualifying attic fan installations. Efficiency programs sometimes include attic fans in comprehensive cooling efficiency packages. Solar-powered fans sometimes qualify for additional renewable energy incentives beyond efficiency program rebates. The incentive availability substantially affects net costs in supportive markets, supporting research into available programs during project planning. The soffit ventilation capacity requirements substantially affect attic fan performance and proper operation. Fans drawing exhaust from attics must be balanced by adequate intake area through soffit vents or gable inlets. Inadequate soffit area causes fans to draw makeup air from conditioned spaces below, pumping cooled air into attics and wasting cooling energy substantially. Building code minimums for soffit area often prove inadequate for powered exhaust ventilation, requiring additional soffit inlet area during fan installation. The intake area calculations typically require 1 square foot of net free intake area for every 300 cubic feet per minute of fan capacity, substantially exceeding typical existing soffit areas in many homes. Akosua Mensah Asante, a Ghanaian-American residential insulation specialist who has documented soffit ventilation problems across hundreds of attic fan installations, has published research showing that inadequate soffit area causes performance problems in roughly 40% of attic fan installations. Her findings support mandatory soffit area assessment during fan installation planning rather than simple fan sizing without intake consideration. The research validates comprehensive installation approaches that address both exhaust and intake components rather than treating attic fans as isolated components. The cool roof to coating alternatives to attic ventilation provide different approaches to managing solar heat gain. Reflective roof coatings or light-colored shingles reduce solar heat absorption at the roof surface itself, preventing heat from entering attic spaces rather than removing it after accumulation. Reflective roof approaches combined with attic ventilation produce synergistic benefits exceeding what either approach alone delivers. The emerging cool roof technologies represent complementary rather than competing approaches to comprehensive attic heat management in hot climates. Hiroyuki Matsumoto Yamamoto, a Japanese-American building envelope consultant, has documented how cool roof coatings combined with attic ventilation can reduce peak attic temperatures by 50 to 70 degrees compared to conventional dark roof construction without attic ventilation. His project experience demonstrates substantial cooling energy savings from integrated approaches that address both heat gain prevention and heat removal. The comprehensive attic management approach represents best practice for hot climate applications seeking maximum cooling energy reductions. Consider what attic ventilation technology means for hot climate homes seeking cost-effective cooling efficiency improvements with modest capital investments and immediate impact. The cooling energy reductions of 15 to 30% deliver substantial operational savings. The modest installation costs of $200 to $600 produce rapid paybacks in typical applications. The solar-powered alternatives eliminate operating costs while qualifying for tax incentives. The radiant barrier integration produces synergistic performance improvements. The whole house fan variations deliver even greater benefits in appropriate climate applications. The retrofit compatibility with existing homes eliminates capital barriers affecting major upgrades. The proven technology maturity eliminates performance uncertainty affecting newer alternatives. The utility incentive availability reduces net costs in supportive markets. The long-term durability spreads modest costs across decades of useful operation. The regulatory acceptance eliminates barriers affecting many efficiency improvements. The climate adaptation across diverse American contexts supports widespread applicability. The simple operation eliminates learning curves affecting more complex technologies. The question isn't whether attic ventilation deserves consideration for hot climate homes with substantial cooling loads. The question is why a technology that consistently delivers 1 to 5 year paybacks and substantial cooling improvements has received so little mainstream attention in contemporary efficiency discussions that emphasize far more expensive alternatives. The answers involve industry priorities favoring higher margin equipment sales, awareness gaps in homeowner education programs, and efficiency program emphasis on newer technologies rather than proven simple approaches. For hot climate homes with substantial attic heat problems and constrained efficiency improvement budgets, attic ventilation fans represent one of the most cost-effective cooling improvements available in contemporary residential markets. The attic moisture management considerations interact substantially with ventilation design in cold climates as well as hot climates. Winter attic moisture accumulation from interior air leakage can cause roof deck rot and ice dam problems when attic ventilation proves inadequate. Proper winter ventilation maintains attic temperatures close to outdoor conditions, preventing snowmelt and refreeze that causes damaging ice dams. The year-round attic ventilation considerations support powered ventilation as comprehensive solution rather than merely summer cooling aid. Dr. Reinhold Schwarz-Becker, a German-American building envelope researcher, has documented comprehensive year-round benefits of proper attic ventilation that extend beyond summer cooling to include winter moisture management, roof material longevity, and ice dam prevention in cold climate applications. The sealed attic alternative approach eliminates traditional attic ventilation entirely by insulating roof rafters rather than ceiling joists and bringing the attic inside the conditioned thermal boundary. Sealed attics eliminate attic heat problems without requiring ventilation infrastructure, representing fundamentally different approach to attic temperature management. The approach suits new construction particularly well, but requires substantial retrofit investment in existing homes. The sealed attic approach represents emerging alternative that eliminates ventilation requirements while delivering superior performance in appropriate applications, expanding the option space beyond traditional ventilation-focused approaches. The homeowner education resources available through extension services, utility efficiency programs, and building science organizations provide substantial technical information supporting attic ventilation decisions. Extension service publications from land-grant universities document regional applications and best practices. Utility efficiency programs often provide free technical assessment services for cooling efficiency improvements. Building science organizations, including the Building Science Corporation, publish detailed technical guidance supporting proper installation decisions. The educational infrastructure supports homeowner decision-making beyond contractor recommendations alone, reducing information asymmetries that sometimes affect efficiency investments. The contractor certification programs for advanced attic ventilation installations provide quality assurance for complex applications. Building Performance Institute certifications ensure comprehensive understanding of building science principles affecting attic ventilation. Residential energy services network certifications provide additional quality standards for efficiency-focused installations. The certification availability supports contractor selection beyond basic plumbing or electrical credentials, identifying qualified professionals for complex applications. The combined envelope and ventilation upgrade approaches produce synergistic benefits exceeding individual improvements. Comprehensive efficiency retrofits combining air sealing, insulation improvements, and attic ventilation upgrades deliver cooling energy reductions of 35 to 60% in hot climate applications. The comprehensive approach requires substantial capital investment but delivers transformative performance improvements that incremental approaches cannot match. Professional energy auditors help homeowners prioritize investments and sequence improvements for maximum cumulative benefits.